Do you ever wonder how we could stop an asteroid heading straight for Earth? Or if we even can? Well, in today's video, I got to sit down with two experts in planetary defense. That's right, defending our planet from space threats like asteroids. And we got to talk about the project they're working on called Pi, which we'll define later, and how this project, or specifically this method they're developing, can help protect our planet from asteroids. The two experts I got to sit down with, and I'll let them introduce themselves and what they do and what their expertise is. But they are one, Brin Bailey.
Yeah, my name's Brin Bailey. I use they, them pronouns. I'm a researcher at the University of California, Santa Barbara, currently focused on the Pi project. And that's really what takes up most of my time.
And again, the Pi project that they mentioned, we'll talk about later and define what that means. And the second expert we got to talk with was Sasha Cohen.
Yeah, my name is Sasha Cohen. I use he, him pronouns. I also work at in Dr. Philip Lubin's group at UC Santa Barbara in the physics department. And I specialize in the hydrocode simulations of our hypervelocity impacts for planetary defense.
And really quick, before we jump into our discussion, I forgot to introduce myself because I forgot that I was filming on a different channel. I am Rachel Phillips. I have a YouTube channel where I talk about all things geoscience. It's called GeoGirl, and this year I am one of GSA's Science Communication Fellows. And for this fellowship, I will be posting some videos onto GSA's GeoSociety channel, and that is what you're watching right now. And in the coming weeks, I will be posting more and more interviews highlighting some of the work that's being presented at the GSA Connects 2024 meeting. So anyway, let's get into the discussion today. So to start off our discussion, let's get some context. What is planetary defense and how necessary is it? Are there any large asteroid threats headed our way?
As we've gotten to understand more about our neighborhood in the solar system, we've learned a lot about asteroids and particularly how many of them there are. At present, we've discovered a little over 35,000 near-Earth asteroids, or NEAs, and we know that there's still plenty left to be discovered. And with that many objects around us, we're bound to be visited by them every once in a while. And while the vast majority of these objects are small and non-threatening, there's always some chance that something larger could come by or something that we don't see coming until it's gotten close to us. And because of this, it's really important that we stay vigilant of what's around us in regard to current threats. There's not currently any large asteroids on a collision course with Earth. And the good news is if something big does end up making its way towards us, we'll know about it far ahead of time because something that's really big really can't sneak up on us. Just in the grand scheme of things, it's incredibly, incredibly unlikely that we will ever experience a fate like the dinosaurs or like the people in Don't Look Up. But in order to make sure that doesn't happen, we have to keep watch.
So thankfully there they mention that we probably won't succumb to the same fate as the dinosaurs, and you guys know on my channel I talk a lot about the dinosaurs and their mass extinction. However, we do need to keep watch. So if we're looking out in space, just how far ahead can we tell in advance that an asteroid is heading our way? And are there any that sometimes we miss that catch us by surprise last minute?
Sure. So it really depends on the size of the object. Something that's larger, we'll see it ahead of time. And something that's, large enough to enact global damage, we'll definitely see years, if not decades ahead of time. Currently, for all objects larger than 1 kilometer in diameter, for all near-Earth asteroids larger than 1 kilometer in diameter, NASA estimates that we have discovered 94% of those in the solar system. So those are really good odds, that we see those, and we can definitely see them coming. For objects that are smaller than that, our awareness certainly decreases the lower that you go down in size, which isn't the end of the world because, if there's a meteoroid that's 3 feet in diameter, we're not worried about that. That's not going to hurt anybody. We usually kind of set a lower limit of about a 20-meter diameter for objects that can start to enact local damage. And objects of that size are certainly much harder to detect in the grand scheme of things. If they're closer to Earth, we have a greater likelihood of seeing them, but there are still some times when we don't see them ahead of time, so it's really important that we keep an eye out, and thankfully there are a lot of missions, current and upcoming, that are working really hard to sort of flesh out this catalog.
Yeah, and one of those upcoming missions is the NEO Surveyor spacecraft, which will improve our situational awareness of these things down to about 140 meters diameter, I believe, is their minimum target. But then, like Brin said, there's this whole kind of middle ground where you don't really have situational awareness of them, but they can still be quite damaging on a local scale.
But before we jump into how we can detect asteroids of different sizes and protect against them when it comes to collisions with Earth, I feel like we need to define what an asteroid is, because I'm sure in different news media outlets you have heard multiple terms for impactors, extraterrestrial things that hit Earth, including asteroids, meteors, comets. So what is the difference between these things? And are we just worried about asteroids, or are we worried about all of them?
So an asteroid is a small rocky or metallic object that orbits the sun. It's usually defined as greater than 1 meter in diameter. And most asteroids come from the asteroid belt between Mars and Jupiter, but some, can come near to or across Earth's orbit. A comet is an icy, dusty object also orbiting the sun. They form in the outer solar system, far away from the sun, where they can collect a lot of ice, essentially. And they normally stay far away from Earth, typically spending most of their time beyond the orbit of Jupiter, if not farther. And when they enter the inner solar system and come closer to the sun, their ice turns from a solid to a gas, kicking off dust and sort of creating that tail that comets are really well known for. A meteoroid, as I mentioned, is a rocky or metallic object that's less than 1 meter in diameter. So those really don't pose a threat, really. And when a meteoroid or asteroid enters Earth's atmosphere at a high speed and burns up, the fireball or the streak of light is called a meteor. And those are what shooting stars are. And if part of a meteoroid or asteroid or comet makes it to the ground, to Earth's surface, that is a meteorite.
Yeah, I always found that funny that we say meteorite for everything that hits Earth. And I'm like, why don't we have asteroids and comites? I don't know.
Just one of those things that, was made up so long ago that nobody, it's just tradition now, I guess.
One other comment regarding the kind of composition of asteroids. Most people think of asteroids as these kind of monolithic rocks, and many of them are like that, especially when you get to very large asteroids. But in particular, the vast majority of asteroids tend to be these very loosely bound rubble kind of gravel piles that are they might be filled with large voids, or they might be made of multiple larger objects kind of loosely clumped together, which is actually kind of a different picture than most people are used to of an asteroid. And it has implications for how you might disrupt it in planetary defense as well.
Oh, that makes so much sense. Yeah, I just did an interview for the Psyche mission, and how that asteroid is so unique as like a clump of metal that might be a planetary core. And I didn't even think to ask, well, what are asteroids normally like? And the accumulated nature, yeah, is very different than what would be a planetary core. And then the last question I had before jumping into the weeds of their project is, how do asteroids get kicked out of the asteroid belt to begin with and begin their collision course with Earth?
The solar system is a totally dynamic place, right? You've got all these fairly, large mass objects in flying around in the form of planets. And when you have a distribution of a bunch of smaller objects which can interact gravitationally with those objects, there come interactions sometimes that will throw them out of their normal orbit and make their orbits intersect with Earth.
Okay, so now that we have a good background about what asteroids are, where they're at, where they're coming from, and kind of a little bit about how they're constructed, let's get into Brin and Sasha's Planetary Defense Project. Now, the reason that I invited them on for this interview is because, as many of you guys already know, I am working with the Geological Society of America this year to promote their annual meeting, GSA Connects 2024, and Brin is presenting their project called Hypervelocity Asteroid Interception and Disruption for Planetary Defense. In the abstract, they and their co-authors submitted to GSA, they talk a lot about their project called PI, which is PI and stands for Pulverize It. And this is perhaps the most self-explanatory scientific method I've ever read about, but in any case, I asked Brin and Sasha if they could just briefly explain what this project is, what it means, and how it works.
Yeah, so the basic process is to penetrate an incoming asteroid with high-speed projectiles. You can think of them like really large bullets, essentially, which would split the asteroid into many smaller fragments or pieces. We design mitigation scenarios such that the fragments are generally less than 10 meters in diameter, about 30 feet. And Pi is a unique method for planetary defense in that it is multimodal, meaning that it's intended for use in a wide variety of scenarios. So Pi could be used whether an asteroid impact is 1 year away or 1 week away, depending on, the asteroid size and speed, among other parameters. And, this really represents the first planetary defense method, which has the capability to mitigate or get rid of threats that we have very little warning for.
So in order to disrupt a target, like Brin described, you have to intercept it with hypervelocity impactors. And it actually works in your favor because in the reference frame of Earth, the asteroid actually comes at you with all the speed that you need. You don't actually have to shoot your projectiles at the target. You just kind of have to put them in front of the asteroid, especially if they're coming at you already. The impact speed is so high that within, the first very short while after impact, the material of the penetrator has been completely vaporized, along with, a lot of material surrounding the impact site. And that vaporized material then expands because it's this hot, energetic gas, and that actually drives the disruption of the asteroid into fragments. But that's, like Brin described earlier, that's just one of the few modes that this system can operate in. You can also operate in a mode where you don't completely disrupt the target. You actually leave some of it remaining. But because of the amount of ejecta that you generate, all of the material you throw off the surface due to this violent impact, you actually get to impart more momentum to the object than you would normally just from the impact of the penetrator. You're actually enhancing the momentum transfer. And that's how the Pi method can work in a deflective mode as well, in addition to a completely disruptive mode.
We hope to be able to also use Pi in a terminal mode or a short warning mode. So Earth's atmosphere kind of acts as a bulletproof vest, shielding us from ultraviolet radiation, typical space debris, and in the case of Pi, asteroid fragments. So in using Pi in the short warning mode, which we refer to as a terminal mode, the cloud of asteroid fragments following asteroid disruption would intercept Earth's atmosphere. But because the fragments are small, rather than hitting the ground, they would fall apart high in the air. And essentially, as the fragment travels through the atmosphere at high altitude, the pressure exerted by the atmosphere will exceed the strength of the rock, causing it to fracture and expand. And as this continues, the fragment will eventually burst or detonate, causing a release of heat and pressure. So as each fragment travels through the atmosphere and bursts, it produces a small amount of light, kind of like a shooting star, like a meteor, and pressure as a shock wave, kind of like a sonic boom. So the collection of these optical and acoustical effects, which we refer to as ground effects, work to disperse the energy of the original asteroid over a wide area of space and time. So we foresee the Pi method as, being able to be used for these short warning threats, these, smaller asteroids that we might not see coming until, they're right there. And as Sasha mentioned, also in an enhanced deflection mode for much larger threats that require a bit more than just a small push.
That was actually one of the things I was wondering is what ends up being, the final effect on the ground. And does that tend to be, essentially no rock material reaching the ground, maybe just like a boom heard, or does some material reach the ground?
In regard to typical asteroid compositions that are more, rocky, those will not end up hitting the ground. They will, in general, always burst in the atmosphere just because the pressure that the atmosphere exerts upon them. For asteroids that might be really, really dense and, very rare, something that's like a pure iron nickel asteroid, which we don't even know if those necessarily exist. But, for this, let's pretend that they do. Something like that has a much higher density and a much higher yield strength. It doesn't want to fall apart, and the atmosphere can't necessarily exert enough pressure to break it apart because of how strong it is. So in a scenario like that, there may be pieces that do fall to the ground because the atmosphere can't, essentially blow them up.
Okay, so as long as like Psyche 16 doesn't come our way, we're good. Okay, so
as long as it doesn't come our way tomorrow.
Yeah. Yeah, I imagine if you do this far enough out, like if you can do it like in space, like is that a thing? And does that like prevent anything from reaching the atmosphere, or is it just like once it's in the atmosphere?
Yeah, that's actually the kind of preferential mode of operation is you intercept the object with as much warning time as you can possibly get, specifically for the reason you just described, where if you can disrupt it early, the fragment cloud can disperse enough to where no fragments can hit the Earth in the first place, and you don't have to worry about ground effects at all. But there are some cases where you just simply can't avoid having to interdict it in a terminal mode.
So essentially, if we know early enough that an asteroid is headed our way, it's far enough away from Earth that we can go, well, pulverize it and no fragments can hit Earth, that would be ideal. But is pulverizing the asteroid our only option? Are there other methods of planetary defense that we are working on developing or maybe have already implemented in terms of planetary defense, specifically asteroid defense? Like, can we change the trajectory of the asteroid somehow instead of breaking it apart into a bunch of smaller pieces? And would that be better or worse than pi?
So it'll depend on a case by case basis, but changing the trajectory of an asteroid is certainly possible, and we've done it. Last year, NASA had their double asteroid redirection test where they tested their planetary defense technology for the first time in a real test, where they sent up a spacecraft to go basically nudge an asteroid to change its path in space. So that is something that we can do and, have physically proven, which is really, really cool. The sort of, I don't quite want to say downside, but the dependency on using deflection to protect us from an incoming asteroid is that you want to know about the asteroid years, if not decades ahead of time, because you need enough time to observe the asteroid, to figure out where it is, where it's going to be, to design a mission. And let's say you have an object coming straight towards you. If we nudge it while it's far away from you and we slightly change its trajectory, in the long run, that'll end up, farther away from you than it would have if, say, you hit it when it was close to you and you change the trajectory, but it doesn't really go very far. So in regard to deflection, you really want to do that as far ahead of time as possible, which, as I mentioned earlier, for larger objects, we'll know about them much sooner. The advantage that we foresee for pi is the ability to use it in a situation where you might not have decades of warning time to prepare. This would be particularly useful for smaller objects, like I mentioned, that we might not see, or objects that come from the direction of the sun, kind of in our blind spot.
So yeah, we can deflect asteroids and change their trajectory, and this can work really, really well if the asteroid's way far away from Earth and we just need to change it a little bit. But as that asteroid gets closer to Earth, you gotta change that trajectory quite a bit for it not to hit the surface. And there becomes a point, it sounds like, that it kind of gets so close that it becomes a little bit late, and maybe pi would be a better option for minimizing the effects of that asteroid impact. But you might be wondering, just how often do asteroids hit Earth? Is pi something we would use very often? Is it something we're already starting to implement?
Yeah, so the frequency at which objects intercept Earth is, again, heavily dependent on their size. For example, every day Earth is bombarded with over 100 tons of like dust and sand-sized particles, whereas, an object slightly larger, like the Chelyabinsk asteroid of 2013, that was about an 18-meter diameter asteroid that airburst over Chelyabinsk, Russia. Something that size is expected to impact Earth between every 50 to 100 years or so. But of course, an undisturbed object of this size would burn up in the atmosphere because it is smaller, and it would not hit the surface, although the effects of a full-sized asteroid airburst are much more likely to cause much greater damage than if we were to break it up. And scaling the size up even more, an object like Chicxulub, which was likely 10 to 15 kilometers in diameter and, responsible for ending the dinosaurs, something like that is expected to have an impact interval on the scale of hundreds to millions of years. So it really sort of depends. And in regard to actually using pi, we likely wouldn't have to use it often, but we believe it would be, a beneficial tool to have in our toolkit.
But wait, does Brin mention there that there's damage caused by asteroids or asteroid fragments that burst in the atmosphere? How can there be damage from an asteroid or fragment of an asteroid at the surface of Earth if it doesn't even reach the surface?
Sure. So bringing up again the Chelyabinsk airburst of 2013, again, that was an 18-meter diameter asteroid that airburst in the atmosphere. And, you have all those cool Russian dash cam, videos of the streak of light that it produces. And so when these events happen, the main effects that, occur on the ground that can provide a lot of damage are the acoustical effects, where it produces, large shock waves as it sort of is breaking apart. And in the case of Chelyabinsk, it shattered windows in over 3,000 residential and commercial buildings, I believe. And that certainly led to, a lot of injuries. And additionally, the streak of light that it produced gave some people sunburns and, temporary optical damage. So, it can burn your eyes as well. And for larger objects, they could even, cause fires. So in designing scenarios for Pi, when we want to break those asteroids up into much smaller pieces, we're designing them in such a way that we really keep those effects, really decreased and to a level that will not harm anybody, that won't cause any fires, that won't, give somebody a sunburn, and that won't blow out any windows. And I can share with you some simulations that we have. So this is a simulation of the ground effects of the acoustics that I was talking about. This is a 50-meter asteroid with an average rocky density that we break into 1,000 fragments one day before it intercepts Earth. And so on the left here, we have the real-time pressure, which shows the pressure exerted by each fragment airburst as it comes in. And on the right is a maximum pressure plot, where each pixel of the simulation holds on to the highest pressure value it has experienced. So here we can see that the pressures are kept, below reasonable levels. So you see here in the maximum pressure, it goes up to about 2 kilopascals, which is the point at which residential windows may begin to break is about 3 kilopascals. And obviously you see here as it evolves, you have all of these overlapping shock waves, which will constructively interfere with each other. So our simulations take that into account. And count that increased amount of pressure. And so in comparison, this is an unfragmented asteroid airburst, again, a 50-meter asteroid with an average rocky density. So we're only going to see one singular burst coming in, but, we see here, we're no longer at 2,000 pascals. We're now at 18,000 pascals, which is a bad day.
So in short, all of the simulations that they've run when it comes to breaking apart asteroids of certain sizes versus not breaking them apart indicate that there would be exponentially more damage at the surface if we didn't fragment them. And with all the windows breaking and health risks that comes with, I imagine it's more of a money saving than money spending venture to implement Pi. But with that in mind, is there a size threshold for the implementation of Pi? Are there asteroids of a certain size or, small size that it's no longer worth it to use Pi? They'll just burn up in the atmosphere and they won't cause enough damage to make the use of Pi worth it? Or do we even know this size range yet that we would use this method for?
Like a 20-meter object is really kind of our lower limit, because that is the point at which an object is large enough to potentially cause local damage. So like the Chelyabinsk asteroid certainly didn't hurt anybody, outside of the local Chelyabinsk area. But that isn't to say that we don't want to stop that local damage from happening. Obviously, if we can prevent it, we would love to. But that really is kind of the lower limit threshold. Anything smaller than that generally wouldn't really cause much of a threat. As we talked about earlier, small meteoroids resulting to meteors that are just shooting stars, those don't hurt anybody.
So size does seem to play the major role in determining whether it's necessary to use a method like Pi for planetary defense against an asteroid or not. However, as we talked about a little bit earlier, asteroids can vary in composition. So does composition play a role as well as size? Or do the asteroids that come toward Earth not vary enough in composition that would really make a difference?
I would say that size is the most, obvious parameter that you can measure and observe. And most of the other parameters are usually much less accessible, such as the interior composition, the density, and all these things. So ideally, you would have a system that would be informed by these parameters, but unfortunately, they're difficult to observe.
All right, so yeah, you mentioned that this is something that isn't currently being done, but is something that is going to be a really useful tool to have in our toolbox. And so what is the timeline in terms of by when are we going to have this tool if it's going to be, developed and everything?
I think it's a little difficult to answer being this early in the development of a project. I think for other methods of planetary defense, like the purely deflective methods that we talked about before, the timeline might be a little bit more clear because they're already in the sort of mission design phase and have done a test mission and demonstrated the efficacy of the concept. I would say, hopefully within the next decade, we would have done some sort of demonstrator mission, which is a proof of concept of the general idea, and that would pave the way for a more deployable, at the ready system.
To kind of expand on that just a little bit, pi is more than just an idea at this point. We've been conducting this research for several years, and we're very fortunate to be funded as a NASA Innovative Advanced Concepts Phase 2 study at the moment, hoping for a Phase 3. And, as I mentioned, we're still fine-tuning the details, but, as I just kind of showed, our results show that the physics are there. We design our simulated scenarios also using pre-existing launch vehicles like SpaceX, a SpaceX Falcon 9 or NASA SLS. So, that technology, of course, already exists. And now we're in the process of, working towards mission design and implementation and, hopefully soon establishing a test phase, as Sasha mentioned.
So the last question I wanted to ask Brin and Sasha is kind of a more fun end of the world question, and that is relative to other world ending or potentially, well, not world ending, but humankind ending scenarios like global pandemics, nuclear war, climate change caused mass extinction. Where do asteroids fall on this list of apocalyptic scenarios? Is their threat to humankind on a level similar to these other things?
Yeah, again, it really depends on what kind of threat we're talking about. In regard to global threats like dinosaur extinction level, we have nothing to worry about. Objects of that size have extremely large impact intervals. They're extremely unlikely, and it's generally not possible for something that big to sneak up on us without our knowing about it, far ahead of time. In regard to regional or local damage, there's definitely a greater chance that we experience an event of that scale. So the world won't be ending due to an asteroid or comet anytime soon, but that doesn't mean that we shouldn't be prepared.
Yeah, and actually, one of my favorite facts to throw around is if you look at the average deaths over time by asteroid strike, or potentially by asteroid strike given their frequency, and you compare it to the amount of deaths by a venomous snake bite, it's actually a comparable threat level. The difference, though, is that snake bites happen with a certain, regular frequency every year, but asteroid strikes are these extremely episodic events where they can be, cataclysmic every time they happen, but the average happens to work out to where they're similar in their threat levels.
Yeah, it's funny you mentioned that earlier when you Brin, were talking about the, the threat being there, not always, but when it is there, we need these things. It reminds me a lot of things like the pandemic and how we have epidemiologists and stuff, even though, maybe there's not anything going on right now, but it could happen in the future. And we need to have people to predict these things and to be able to defend against these things like asteroids. So it is funny how it's, we look at these things and we're like, but we don't need that right now, but we will. So
yeah, we might not need it now, but we might not know when we do.
Exactly. So yeah, but I think this was such a great conversation. Thank you both so much for coming on. If there's no more parting words, then that concludes our interview. And yeah, just thank you so much.
Awesome. Yeah, thank you so much for having both of us. This was really fun.
So I guess we don't have to worry about succumbing to the same fate as the non-avian dinosaurs. But it does seem like it's a pretty good idea for us to protect against local and regional sized damage from asteroids. So I hope you guys enjoyed learning about the PI method for planetary defense. I love both the acronym and the actual name, Pulverize It. They're both so good. Anyway, if you want to check out resources related to this project, Brin sent me a whole bunch of links to web pages with amazing graphics, to a YouTube channel where they have a bunch of videos like the ones they were showing earlier with the different possible scenarios, whether it's fragmented or unfragmented, how the pulverization of the asteroid would play out in terms of the simulation, and all of that. Really, really cool videos on that channel. I checked it out and was on it for longer than I should admit. And they sent me 2 links to articles related to this project, but there are many. And of course, if you want to check out their presentation at GSA, I will put up the time and day that should be if you are attending GSA. And lastly, if you want to keep watching videos here on YouTube about asteroids, as I mentioned in this interview, I talked to Dr. David Williams recently about the Psyche mission to asteroid 16 Psyche, which is a metal asteroid made mostly of metal, which is like insane and a type of world we've never been to. So if you want to check that out, I will link that video up on the screen for you. And with that, guys, thanks so much for watching, and I'll see you guys in the next one. Bye.